Okay, good. So just to start off, there is one suggestion which I think would be very useful is that if there are I mean, there has been a steady set of very useful questions. Maybe what we can do from today onwards is that if the questions are not directly related to the understanding of what we are discussing, maybe we can hold back those questions till the end of the course. I mean, you can write all those questions in the chat. It's just that I'll take them up at the end of today's lecture. So that way, I'll try to finish by say 12, 15, 20. And then we can continue with the questions. That way, we can basically try not to miss out people who have a deadline of 12:30. Okay, so that I think has been an issue in the last 2 days that we have been overshooting, and I'll try not to overshoot. And then we can, of course, continue till we discuss all the questions. Okay, so that's having said that, let's just start with the third lecture, which we based on the things that we had discussed yesterday. So we will start with the classification of closed curves on a plane, and we will generalize these ideas. And we had got these two examples that we worked out. One is the Aharonov-Bohm phase, and the other is the magnetic monopole. And we are going to try and make mathematical generalization so that we can use these ideas in other settings. Okay. So having said that, are there any pressing questions to start with? Okay, so yeah. So if there are any pressing questions from yesterday, let's just take them right now, and then continue. Otherwise, we will. Yeah. So okay. So are there any questions? Okay, good. So it seems that there are no questions. So let's go back to what we were discussing.
Subhro, there's one question, I think.
Yes. Okay. So let's take that. Okay. So there is a question by Steffi Jones. I have a doubt from yesterday's discussion about Aharonov-Bohm phase. We discussed Aharonov-Bohm phase as an example of a Berry phase, but Aharonov-Bohm phase is path independent or not topological, right? Aharonov-Bohm phase is a quantum phase shift that pops up when the particle traverses a closed path around a region of confined magnetic field. Does similar phase shifts arise if excluded regions, if the excluded region is a confined electric field? Yes. So there are similar effects which goes under the name of Aharonov-Kasher effect, which have similar issues where which are extensions of the Aharonov-Bohm phase, which I would urge you to read up. And these are examples of Berry phase in this, as you pointed out. These are path independent, and a part of the Berry phase is an example of a topological phase. If we reach a discussion about quantum Hall effect, we will see this distinction. But for the case that we had discussed, where we had thrown away the kinetic part, etc., this whole part is basically a topological phase, because it only depends on the topology of the paths that's traversed by the particle, the relative the loops that are covered. So that's the comment. Okay. Yeah. So more questions? Okay, good. So let's see. So let's start with this. Just a moment. Okay, good. So let's go back to my slides. Okay, so so we started out taking clues from the Sahana-Bohm phase that it depends upon the path and the topology of the plane. We sort of motivated ourselves to try and study the problem of classification of closed paths, at least on a plane, and then the idea was that once we classify these closed paths, we would like to associate a robust invariant like the phase phi in the example that we saw, okay, with each of these class. And first we would like to, so comparing closed loops which do not intersect, like different closed loops lying on a path, is immediately very difficult. And what we wanted to do is to basically compare curves, only closed loops which have a common point. Okay, so various closed loops which meet at a common point or pass through a common point, which we are going to call a base point. Okay, so this base point can be any point, but let's just fix one. Okay, and we want to study first how to classify closed curves with a common base point, and then we would like to see how to, once we know the information of how to compare how to classify curves with a given base point, how to change the base point. Okay, good. So that's what we will start with today. And the aim of this lecture would be to reach a stage where we would be able to find out context where we can ask all these Urna-Bohm type of questions or generalization of that by the end of today's lecture. For that, we would need to develop some mathematical ideas. So that's what would be the most of today's lecture, at least the first 2/3 of it. And then in the last third, what I'll do is to bring out the context in which these happen generally. And tomorrow onwards, we will exclusively focus on order parameter fields and their topology. Okay, good. So okay. So then we realize that in a two-dimensional plane with a given base point, we can draw all curves by parametrically by this set of equations where tau is a parameter, and the base point is we start all the curves at the base point. Okay, and given that we have a function, these are directed curves. Okay, which we sort of discussed yesterday. And oppositely directed curves are counted as different curves because they are given by different functions. And we will be interested in closed curves where not only the starting point is the base point, but also the end point is the base point for all curves. Okay, and this we discussed yesterday, and soon we found that this is too restricting. Okay, because if we try to define a composition to give some mathematical structure to this set of curves, then we found that there would be at least one point in the middle between tau 0 and 1 where the two curves must come, the composition curve must also pass to the base point. And if we keep on doing this, it has to come back to the base point more and more times. And this certainly does not include all the curves that are passing through the base point, and is not a very useful composition rule. It is some composition rule. We can go ahead and do our algebra of curves based on this composition rule, but it's not very useful to us. And the reason why it is not useful to us is that it is too detailed. We are considering each curves individually, and therefore the Urna-Bohm phase really does not depend upon that, as we saw, at least in the limit that we can throw away the kinetic term completely. Okay, so but that's the limit that we would like to understand. where this effect is most pronounced. Okay, so then what we did is to define something called a class of curves, or to be precise, a homotopic class of curves at a given base point, which means that this is a subset of curves passing through I, which can be continuously deformed into each other. Okay, we already defined that context. We already defined that concept of how to continuously deform curves into each other, and by this square bracket f, what we mean is all the set of curves which closed curves which pass through the base point I and can be continuously deformed into each other using another parameter like eta, as we had studied yesterday. Okay, and what we realized is that this forms an equivalence relation, and each homotopic family of curves form an equivalence class, and in that context we defined an equivalence relation. Okay, so I've been similar to this set of equation, the relation, these properties, I'll be defining keep on defining a set of properties as we go on today, and these are mathematical properties which are useful, and I mean, of course, if you're familiar with it, you know how to use these words. But if you're not familiar with it, then you might have to go back and forth to understand this, and maybe that you can do that after the lecture today. And it's just a language. In the same sense, we all face this. No, when we say that we are in an inertial frame, okay. So then we all can use Newton's laws, etc. So the concept of inertial frame is a very useful concept. Okay, in that sense, these mathematical concepts, when I say equivalence class, etc., etc., these are useful concepts. Okay, which we would need, and that's why I want to introduce all these names so that I'll sometimes use it. But when you go back and try to extend your knowledge on this, you exactly know what people are talking about. So it's to get familiar with the way of speaking and try to put things in perspective. Okay. So we found that this homotopy family forms an equivalence class of all the set of curves that passes through the base point I. Okay. And we explained all these things except for this point, which I'll come to. Let's go on. I would have to explain what a quotient set is, but let's. Okay, good. So this is in figures. What do I mean by composing curves and continuously deforming? So a one parameter example of continuous family of curves is something like this. There are two curves, f1 and f2, which I'll call would belong to the same equivalence class of homotopy curves based at I. Okay, when I can find a family of parameter like eta, okay, such that for eta equal to 1, I have f1. For eta equal to 0, I have f2, and I can continuously vary eta to generate all the intermediate curves, okay, starting from continuously deforming 1 to 2, okay, and this is what this equivalence class means, okay. And now the composition, which we found that if I had taken two curves, so that's these black curves, f and g. Okay, so if I had composed them together, I would have got this curve which both meet at this point I in the middle of the parameterization tau. Okay, but when we say that I have this family of curves which are homotopic to this black figure of 8 curve, okay, then I mean all curves which I can think about, all closed curves which I can continuously deform from this black figure of 8 curve, continuously keeping one of the base points at I, where we can start with drawing this curve. Okay, so that's this blue dotted curve that we have drawn. So I'll say that FG is this, sorry, no. Okay, so that's this black curve, okay, but this is homotopic to all this blue curve, okay, so let's call that F tilde, okay, so that's this blue curve, okay, so they are equivalent because they can be continuously deformed into each other, okay, so that's this statement that this blue curve belongs to this family which is generated by the combination of the individual curves F and G, but can be continuously deformed. Okay, so that's in picture what this mathematics is suggesting. Okay, okay, good. So that's the composition rule. Okay, now you can see that I can freely extend that composition rule to an associative law. I can first combine two curves. Okay, and then maybe I can draw, let me choose a, okay, so I can draw a curve which looks like this, okay, so that's FG, and then if I have another curve which looks like this, okay, I can combine the F curve with the red curve with the black curve and continuously deform it, and you would find that that gives us to an associative law which is much less restrictive than the individual curves. Okay, okay, good. So so you would find that generally if it is if there are no holes, etc., we can combine all these curves and sort of shrink them, continuously shrink them to the point that to a curve which basically never leaves the base point. Okay, so all curves which are homotopic, which are the continuously deformable to this curve, which is basically a point at I, okay, which stays there, belongs to the identity class. Okay, that defines the identity of curve of this whole set of curves. Okay, and clearly there is such a class which contains the identity, all curves which can be continuously shrink to the base point, all the subset of the curves. If there is a hole, then of course we cannot shrink, but there is always a subset of curves which we can shrink, and so in that sense this set of curves contains an identity. Okay, so of course it also contains an inverse now, that the curves which go opposite to each other, and you can go and draw, and I'll give you more and more the hints and not draw these things, for where if you compose a curve and it's the inverse, you would get the identity curve, or a curve which can be deformed to identity, and hence this also contains an inverse. Okay, so so that's the rule, and so therefore this set of homotopic closed curves were based at point I forms a group. So these the rules, the closure that we have defined, the associative law, the existence of identity, the existence of an inverse, all these composition rules allows us to endow a group structure to this set of homotopic curves, and this group is called the fundamental homotopic group, or the first homotopic group, and is denoted by pi1 of mi. Okay, so pi1 is the notation. Okay, m is the space in which the base point lives, okay, which is okay, and the I here is to denote that these are homotopic groups of curves based at point I. Okay, so that's essentially the statement that all the homotopic curves at base point I forms a group which is denoted, which is called the fundamental group, and this is the notation. This is just a notation by 1 of mi. Okay, good, and the space. So the particular kind of space in which our base points live, and in most of the physics, the base points live, is called a manifold. Okay, and remember we had encountered these words. Again, these are in similar notations. We are not going to prove it, prove things, but we are going to use these ideas, which are very useful. Okay, and I'll soon show you examples from various areas of physics which contains study of manifolds. But manifold is a concept that it is really a space. I mean, all kinds of space you can think of, which locally looks like a Euclidean space or a complex space. Okay, and hence it is locally continuous. So Euclidean space is continuous and smooth, that is infinitely differentiable locally, at least. Okay, so it might be globally smooth, etc., etc., but then we have to allow for holes, which is why it may not be globally smooth, but we have to I mean, locally it's still smooth except for on the boundary of the hole, etc. So so that's the definition. That's a loose definition of manifold. We can make it slightly more pointed by defining open sets, etc. But we won't need that. You can sort of make this more sophisticated by yourself. But this is what we would like to understand. Okay, so examples of such manifolds are various in physics. So I mean, as we'll find that the E and the B field that we have discussed, our space-time is a manifold. So R belongs to R3, okay, or RD, okay, this position. And if we go to relativity, we have to include time. So space-time is a manifold. The E and B fields live in a manifold. The theta phase, the flux that we saw, lives on a manifold, which is actually a circle, because flux is only defined 0 to 2 pi. Okay, so there are various examples of manifold which we'll come to in a moment. But essentially, what we would like to point out that in a large context of these theories, we are concerned with trying to understand the properties of this manifold. Like in the Harnack-Bohm case, we are concerned with the understanding the property of this the plane with or without holes, or how many holes, etc. So this is one thing that we want to try and understand. But in general, just deviating from what we are trying to understand, the manifolds actually have 2 point of views of understanding. Okay, 2 extreme point of views of understanding. One is that given space, we can try and understand the properties of the space locally. So I draw a small sub-region in that space and try to understand that locally. Okay, and this is what I think our mathematical physics teaches us a lot of. That's the physics of vector space. Okay, so what we do is that we draw all kinds of tangents on that small. So since this looks locally to be a Euclidean or a complex plane, we can draw tangent lines living on that plane, and then try to study the properties of those tangent lines. And this is one way of locally trying to understand the space. Okay, and of course we can take a global point of view, or a much more non-local point of view, in the sense that we are not interested in what is happening to each of these small patches, but some gross properties like can I close all loops and deform all of them together? Are there holes, etc., etc.? And those are typically formed under these ideas of topology. And of course, you can see that these are not really independent. Okay, and this, as you know, the simplest example of this, and I won't go into the detail, is that if you take a tangent plane on a sphere and try to rotate it, you generate parallel transport. And this means, whereas on a plane, you do not generate parallel transport, and which means that it is sensitive to various kinds of global features. Tangent planes are also sensitive to various kinds of global features, and these two things are related at some level. Okay, so there is a very well developed branch of mathematics which tries to understand these properties of manifolds with or without holes, etc., from both the local perspective and from the global perspective. And some of you, if we know, as physicists, we have learned in our mathematics classes, and some of it we need to try and brush up. Okay, so what we would try to concentrate on are these global properties, and this is what we are now going to focus on. Okay, so so we can try and understand this. Let's start with our example. So in our example, the manifold is this. So that's the single plane with a single hole at, say, R0, okay, in the region surrounding R0. So the manifold contains of, in a slight abuse of notation of the manifold, I think, so this R2 is basically the whole two-dimensional plane, okay, infinite plane. And I have taken minus R0, means that I have taken out a neighborhood of region around R0 where the hole is, okay. So that's what our manifold is, a single with a single hole, and I have taken out that region because that's forbidden for the particle, okay. And in this case, we can ask what is the homotopy group, the first homotopy group based at point I looks like, okay. What are the equivalence classes, okay. And we find that in terms of the phases, it contains the phase gain. It contains this number of elements where, depending upon if I don't close the loop, don't go around the hole, I do not gain a phase. If I go around the hole in one particular direction, I gain a phase of plus phi. If I go around in the opposite direction, I get a phase of minus phi, and so on and so forth. If I go in this direction twice, okay, I gain a phase of plus 2 pi phi. There is this hole here, and if I do it in the opposite direction, I gain a phase of minus phi. So depending upon the phases, it is basically this is the set of elements that I generate. I can associate with each of these set of homotopy curves on this plane. Okay. So then the first homotopy group is okay. So this n integer is basically the number of times I wind in, say, I fix a convention. The number of times I wind in the anti-clockwise direction minus the clockwise direction. Okay, and so one would be an example. So suppose if I take this curve I go around in this direction, okay, and then I turn back. So, okay, so you see that I went around in this direction once, so anti-clockwise 1 and clockwise 1. So the net thing is 0, okay. And so then it's an exercise left to you that this can be shrunk to an identity map. Okay, so you can define a parameter. So it is homotopic with this curve. Okay, so what characterizes this whole set of homotopy curves with a single hole is basically this integer which acts as trying to tell us the number of times the curves or the family of that particular homotopy class winds around that hole. Okay, and then we can see that if I take a curve with n equal to 1, okay, that's this curve, okay, that's say this curve, okay, and then a curve with n equal to -1, okay, we should be able to prove that we can deform this, compose these two curves -1, okay, and compose these two curves to get a net curve of winding 0. Okay. Similarly, if I take a curve with n equal to 1 and another curve with n equal to 1, then I can define the composition rules and deform it to a curve with n equal to 2. Okay. So in terms of the winding numbers, which form the first homotopic group of this space with one hole, it is an abelian group which is closed under addition. Okay, so these integers n form an abelian group which classify all the curves based at point I, and that forms the group of integers, which is what. So in short form, what is denoted is that for our case, R2 minus R0, okay, is equal to Z. Okay, so that's the statement, that it is a group of integers. Okay, so now is a good time to try and answer some of the questions. Okay. Okay, so there is a question that by Mrinal Kanti, who says that I'm not being able to understand the direction of the combined curves. Okay, so let's try and try to address this question. Okay, so suppose I have a curve I, okay, and a base point I, and then there is a curve f, okay, which is with a given direction, okay, and then there is a curve g, which is with this direction, okay. So the combination f dot g is as follows. Okay, I start with this, okay, go along all the way, sorry, following the curve f, okay, and when I arrive here, okay, so remember the direction to continue is this. Okay. That defines this curve. Okay, so I could have taken a different g which has the opposite direction and composed it. Okay, it just depends upon which two curves I take, and that's what I would like to define. Okay, so does that answer your question? Okay, okay, then there is a question by Arpon Sinha. Identity will be a point. Yes, identity is a point which never leaves the base point, and all curves which are continuously deformable to this point belong to the same homotopic class. Okay. So there is a question by Tista. Can there be nth homotopy groups? If so, what is meant in this context? Yes, there are nth homotopy groups. I'll come to that in a moment. I meant to come to that in a moment. Let's just wait for that. Okay. So then there is a question by Shubhastri, which given n, can there be different given n, can there be different combinations of n anti-clockwise and clockwise? There can be different combinations of n clockwise and anti-clockwise, right? And there would correspond to different kinds of windings. So what information do we get given just n? Yeah, so so the n, remember, can be a positive. Yeah, so n let's go back to this. Yeah. So so n is this phase, okay, which characterizes the physical. So remember, this is a physical observable thing, okay. So so this is a physical. This n phi is a physically observable phase, okay. So it is neither sensitive to n clockwise, nor it is independently sensitive to n anti-clockwise, okay. It turns out to be sensitive to this particular difference, okay. And that's why we are in this case we are trying to sort of focus on this particular integer, okay. If you can come up with a case where I should be able to, I should be careful about distinguishing between the clockwise windings and the anti-clockwise windings, then of course this way of doing things does not work, and we have to make our the calculation sensitive to that. But as far as this 100 ohm phase is concerned, we are fine with the net winding, okay. And in fact, what we have seen is that this n clockwise and n anti-clockwise are not topological objects, okay. So in the sense that they are not robust, because I can continue, I can sort of what is preserved is the net clockwise winding. So suppose I take a curve where the n anti-clockwise is 3 and then the n clockwise is 1, okay. So the net winding is 2, okay. I can continuously deform it to a curve where n anti-clockwise is 2 and n clockwise is 0, okay. So this would, these two classes would be homotopic. So in that sense, n anti-clockwise and clockwise do not have a distinction in terms of the kind of topological features that we are considering, and hence we should not be able to distinguish them, and clearly we cannot distinguish them with our physics, okay. So it's self-consistent, okay. Mathematically I can still ask the question, but yeah. Okay, good. So there is again a question by Tista. Is there a hole in the, if there is a hole in the 2D surface in 3D space, then phi should always be 0 due to the extra direction? Yes, we will of course see those kind of things. Let's just wait. I think these are all fantastic questions. It's very good that all of you are preempting directions that we are doing, which might mean that I'm teaching things which all of you know, which is great to see this. But let's see. We will try to do that. Okay. So Tunil, you have a question.
Yeah, so this is a slightly speculative one. So do we expect all the homotopy groups of different points in the manifold to be the same?
Yeah, I'll come to the
okay,
that.
okay. Yeah, okay.
Yeah. Okay. Good. So okay. Okay, so so let's start by addressing generalizing these questions further, starting with what Tunir had asked, the different fundamental groups at different base points. Okay, so suppose I have fundamental, I know the fundamental group at base point I and the fundamental group at base point G. Okay, so then what I can define is what is called a path isomorphism. And let's just use a word, it would be clear what I mean, is that I think about, so that means that I know how to classify loops with this base point, okay? And I want to know how to classify loops with this base point, okay? So then what I can draw is sort of a line, okay, which comes and goes back, this area to be vanishingly small, okay? As long as I can draw a line, then you see that any loop, I'll draw one, okay? And this I'll call, okay, J, I, okay? So then you see that I can draw this loop, okay. So if this loop was F and this loop was this line was L, okay. So then I can draw this closed loop G, which is equal to L F L inverse. Okay, so L comes in this direction, say F goes in this direction, and L inverse goes in this direction. So that's a closed loop again, but with base point F. So if I can do this to all these loops, okay, then I get the class based at J, and then I can do this independently to all the class of loops, and I'll get a fundamental loop based at point J. Okay, so that's what those are the kind of ideas we can use, and the particular construction that I have used is called a path isomorphism, which you can read up. I'll give you references at the end, but that helps us to, as long as I can define a path isomorphism, which means that this procedure that I just outlined is a well-defined procedure and I don't encounter forbidden regions. So for example, what can happen is that between I and J, there is a line singularity. Then I cannot draw, then I cannot join I and J. Okay, I cannot draw lines crossing the singularity. So that is an example where I cannot find a path isomorphism, and then I cannot compare the homotopy group based at I and based at J. But as long as I can find a path isomorphism in the sense that I can draw a continuous path like this, a closed loop of vanishing area between I and J, I can always extend the first homotopy group based at I with the first homotopy group based at J, and so on and so forth. Okay, so that's the way to generalize, and that once I know this, how to do this for 2 points, I can do this for 2 arbitrary points which are connected by a path isomorphism, and that gives rise to the fundamental abstract fundamental group. Now I have removed the base point, and that means that by looking, this is why we started out with the fundamental group at the base point, and then once we know that, we know how to know it for different base points. Okay, good. So okay, so so that's the definition of the first homotopy group. Okay, good. So is that fine? Okay, so questions. Okay, good. So then let's move on. So now to answer now to extend these ideas, and we can define higher homotopy groups. Okay. Which are given by pi of n of m. Okay, where n is, so let's let's keep 0 aside. Okay, let me just make a comment about 0 too. Okay, so 0 means disconnected space. Okay, and we will see an example when we come to Ising model. Okay, one we have already learned. This is a classification of closed loops. Okay, so by pi 2, what we mean is classification of closed surfaces. Okay, of course, you can see that we can only go to pi 2 when we are in d equal to 3. Okay, then what we can do is that repeat all our calculations. So take a base point I. Okay, now define a function f. Sorry, I don't want to draw a vector here. Okay, a function f as a function of 2 parameters. So tau is now tau 1, tau 2. Okay, where tau 1, tau 2 both belong to 0 or 1, okay, and I can vary both of them to generate a surface, okay, and I can demand that the surface at at f of 0, 0 is equal to I, okay, and that's a starting base point, and equal to f of 1, 1. So they come and meet at the same. And thereby I can generate closed surfaces, and then I can ask, okay, can I generate closed surfaces, homotopy classes of closed surfaces, okay? So that means closed surfaces which I can sort of continuously deform into each other. Okay, you see that this is, once we understand how to do this for closed curves, only the diagrams become more complicated, but at our level of doing things, we can think about doing this, extending this procedure. Okay, so then in 4 dimension, we can think about pi 3, okay, which is classification of volumes. Okay, so so we can keep on doing this. Okay, and this would give us we have the first homotopy group for pi 1, and we have closed surface, which is the second homotopy group. We can have the third homotopy group, and so on and so forth. Okay, all these homotopy groups would be useful as we go ahead. And this, knowing features of all these homotopy groups, would give us an idea of how does the gross features of this space looks like. Okay, so let's see an example of the second the homotopy group. Okay, so let's think about a 3-dimensional space R3. Okay, so that means that I have infinity in 3 directions. So R3 is specified by x, y, z, where each of them x, y, and z lives between minus infinity to infinity. Okay, so this is also a projective sphere. Okay, but so that's let's try to ask what is pi 1 of R3. Okay, by the way, what is pi 1 of R2? Okay, so that is just a plane without any holes, and there we know that given any base point, I can sort of continuously form any point to identity, and it's a trivial group. Okay, so that's denoted by this, that it is a trivial group and it only contains identity. Okay, so that's, so similarly pi 1 of R3, okay, is 0, because I can so given a 3-dimensional space, okay, I can continuously deform all loops based at I to identity. Okay. What is pi 2 of R2? It's also 0, because I can draw closed surfaces. Now my drawing is going to fail me. I can draw closed surfaces, spheres, okay, and continuously shrink them, keeping the base point. Okay. Good. So now we know how to do this, and we can keep on doing this for Rn. Okay. What about a manifold which is R3 minus, say, I take out 0. Okay. So this turns out to be a very important manifold. Okay. This is exactly the manifold which determines the, when applied to many body wave functions of identical particles, this manifold determines the fermions and boson statistics. Okay. So, okay, we won't be able to go into that, but you can read up. But here, what I have done is that I have taken all space, but I have scooped up R equal to 0. Okay. So then you see that if I have a base point, and these are now 3-dimensional loops, okay, I can always draw loops, okay, whether it encloses this zero in a sense of a plane or not, okay, I can continuously deform it, because I can think about this is the XY plane, this is a 0. So if I draw a loop like this, okay, and this is what I think this was pointing out, or someone was pointing out, that I can lift this out of the three-dimensional space, because my space is three-dimensional, and then I can think continuously deform it into the loop and then shrink it down to 0. Okay, so pi 1 of this m, based at I, sorry, is still 0. But what about pi 2? Okay, so pi 2 of go ahead and calculate, and okay, you can see that I cannot, it is certainly not 0. Okay, I won't tell you the answer, but it's certainly not 0, because if you have this and you have a base point and you draw a surface, okay, it's like having a charge and drawing a Gaussian surface. I cannot shrink this surface to 0, okay, but if I draw this surface, okay, I can shrink this surface to 0. So at least it has two kinds of surfaces. These surfaces can be deformed into identity. These surfaces cannot be deformed into identity. Okay, so that's essentially what you would need to understand to try and see in 2 dimension whether there are bosons or conjuncts, etc. Okay, good. So we can go on and play this game, and I'll give some exercises, okay, but let's move on. Okay, so at this point, are there any pressing questions? Okay, so there is a question by Tunit. Tunit, please go on.
Yes, I'm a bit unclear about the composition of these two-dimensional surfaces. Like for one-dimensional curves. Yes.
Yes.
So we defined a composition rule for these loops, where we said that the function goes with double the speed. So how do we do that for two-dimensional surfaces?
Yeah. So we have to be more careful. We have to suppose I have a sphere like this, okay, at this base point, and we have a sphere like this at this base point, and we define a way of doing this. Now, the direction, what was used to be a direction on this for the loop, has to have a general connotation depending upon how you do this parameterization. Okay, so whether you draw the surfaces patchwise, and how you from a given point, how do you go in different directions? Okay, so that's given by this parameterization. Okay,
right.
So when you try to compose two surfaces F and G, okay, what you have to make sure is that when you finish composing the surface F and you start with the composing the surface G, then this tangent plane has to have a common has to be common at this composition point. Okay, just like in this case, what happened is that there was this direction, okay, or the tangent plane, which you sort of started here and ended up here, which gave you a unique way of composing things. You have to sort of line up the tangent planes. Okay, so that's the way you one should think about it.
So, but what do the tangent planes have to do with it? Because I could compose two of these closed curves such that tangent planes at the ends would not line up even. I mean, even that would be possible, right?
Yeah. So this is the reason why defining this whole classes are useful for us.
Okay. I see.
So that's the reason why to sort of make simple composition rules available to us. We want to think about not of a particular surface, but a family of surfaces.
All right.
And,
okay, all right.
It's a crude parameterization, but that's what we.
Okay.
Yes. More questions. Okay, good. So, okay, so let's move on. Okay, so so now what we given that we have this group, the next thing we need to notice is that so we have achieved the first task that we were set to, which was like let's see, so classify closed curves. Okay, and then we need to understand this, generalize this part, associate robust invariant like the phase. Okay, so that's the second thing that we would need to learn now. Okay, good. So so this part is much easier, and things that you know is that for every homotopy class, as we have said, we have associated a winding phase, net phase, which is n into phi. Okay, so in that sense, it means that every closed curve, okay, is associated with a phase, and that's an example of what is called a map. Okay, so we have a set of objects to which we associate another set of objects. Okay, and in general, we can generalize this. This you know that we have a set X and have a set Y, and can define a rule F, such as say y equal to x square, and define a function. Okay, so this should be thought of, this map. This function should be thought of as a, sorry, there are too many f's, so this is a function f. Okay, this is a curve f. Okay, so one can define functions. These functions are maps, examples of maps. Okay, and so once we classify the set of curves, we can associate certain numbers like n of phi in this case through a particular map, and the nature of the map is what physics tells us. So remember, we associate this phase from our knowledge of electromagnetism. So the nature of this map is dictated by physics. Okay, and so there are various kinds of maps. I won't go through this. These are things that you know. Again, the point is that it is a way of speaking. So just as you, the example that I gave you, just as you, when I say inertial frame, you know what exactly I mean. So similarly, if you're in this field, if I say you injective map, then it means certain things, and it is useful to understand this. But I'll not go through these points, and you can. I encourage you to read them, these things up in this context, such that you know exactly what they mean. Okay, and most likely you know all these things. Okay, so so we now have completed the two different things that we were set out to do. Classify the closed set of curves, and how to extend it to surfaces and volumes, etc., etc. And then the concept of a map, which the relevant physics should tell us how to do, and what is the particular map that we should define, so that we, with each closed, with each homotopy family of curves or surfaces, we can associate a robust quantity which does not change within the homotopy family. Okay, so remember, this n phi does not change within the family. If I change the family of f within the homotopy classes, within the same homotopy class, it does not change. So in that sense, n of phi is a robust quantity. Okay, so we have achieved this rough way of classifying things, average way of classifying things, and in a sense, we have learned how to deal with the topology of manifolds in one particular way. Okay, which is a homotopy classification. Okay, so we will now try to use this in other physics context. Oh, I see. There are two things that this I already pointed out. If there is a 0 holes, the pi1 is 0, and such that there is one identity element, and this is called a simply connected plane. Okay, and then if there is a 1 hole, we have this, and we need one integer to specify it. That's the integer in this group, and it is called a multiply connected plane where the multiplicity is 1. Okay, now what about n holes? Okay, this was one of the questions that was asked yesterday in a different context. Is that suppose I think about n holes in this plane, okay, and each carrying flux phi I, okay, phi 1, phi 2, and so on and so forth. Okay, so repeat this calculation, keeping only the very phase term, and you would find that for this can be deformed with all the knowledge that we have acquired. This can be deformed into the class of paths, okay, that within each homotopy group, and each of this class contributes a phase where phi I is the phase of each of these holes, and ni is the total number of windings around the net number of windings around these holes. Okay, so that's the phase. Okay, so now you see, to specify the pi I need to specify for each class this whole set of ni's for each of the hole. Okay, so in other words, I need to specify n numbers, okay, each of which are integers, both positive or negative. Okay, so for example, 1 0 0 0 0 would mean that it just goes around the whole number 1 once. Okay, and this is okay. Again, a good thing to think about is to compose such numbers, each of which forms an integer, a set, the ordered set, like 1 0 for 2 holes and 0 1 are different things. Okay, so it's an ordered pair, and such ordered pairs are called Cartesian products. Okay, so what we need is now n-dimensional vector. Okay, and one can form a lattice out of this n-dimensional vector. Okay, and that forms a group. That forms a first homotopy group, okay, of n holes. Okay, in particular, you should consider 2 holes. Okay, this is called the famous figure of 8 group. Okay, and so that means that I have 2 holes, hole 1 and hole 2. Okay, and I consider psi I, and I can have paths going like this, which are say this is hole 1 and this is hole 2. So this is characterized by 1 0. Okay, and this is characterized by 0 1. Okay, so I associate no longer numbers but vectors. Okay, and you should be able to prove that this is actually a non-abelian homotopy group. Okay, so yeah, so this is that means that you should not be able to deform all curves with the same homotopy number, and it would depend upon the way that you would compose these curves. Okay, so just go ahead and try that. Okay, good. So so with those examples, what we have now achieved are the twin goals that we had started out with, and we are now ready to apply this to physics settings. Okay, good. So okay, so at this point it's useful to take questions. Okay, so questions. Yeah.
Okay, so yeah, I have a question regarding the 2-hole problem. So let's say
Yes.
yeah, so every homotopy class is defined by 2 integers. So 2 comma 2 should be a valid homotopy class. But when I say 2 comma 2, does that mean that I'm making two loops across the first hole and then 2 loops across the second hole? that would be a valid element in that class. However, if I make one in one hole, one in the other, and then one in the first and one in the other, that should also go to 2, 2, right? But they don't seem to be continuously deformable to one another.
Say that again?
Yes. So I'm describing 2 elements in the homotopy class, 2, 2.
Yes.
The first element is the one that makes 2 loops around the first hole and then 2 loops around the second hole. And the second element is one that makes alternate loops around alternate holes. So 1, 1, 1, 1, like that. They don't seem to be continuously deformable to one another. However, both of them seem to be 2,
so 1, 1.
Yes.
So these are different, right?
Oh, so composing 1, 1 with 1, 1 itself is not 2, 2.
Yeah, so this is what I said. Just draw these things, I see. Okay? So you would find that this is the comment that this is a non-abelian.
I see.
You would not be able to add integers in the sense that you would we just added. Okay? So one has to be careful.
Okay.
Okay? So yeah, I think that this is famous. This group is famous enough. You can Google, but I would urge you to try and do this yourself. Yeah. So the rules of addition needs to be modified. For how you compose is important. Okay. So okay. Let's go back. So we want to generalize. Okay, further. Now, so having generalized the mathematical things, we want to generalize the physics. Okay, we don't want to remain confined to electromagnetic theory. And to this end, we have to the aim of the next, say, 10 minutes is to formulate the question as to where we can find these manifolds, this context where we can define manifolds and these kind of maps whose topology would be interesting. Okay, so this is the problem that we want to try and understand. And okay, so we would concern ourselves with many body systems, mostly taken from classical and quantum StatMech, almost exclusively from classical StatMech for the next 2 classes. Where by many body we would mean typically 10 to the power 23 the particles or degrees of freedom. Okay, and as you know that specifying many body systems require roughly 3 ingredients. Okay, this is one way of putting things. One is the degrees of freedom. I mean, whether you are dealing with classical particles, classical spins, bosons, fermions, whatever, okay, you have to specify what those degrees of freedoms are. Okay, and often, as you know, that these degrees of freedom depend upon the effective energy scale which we are treating them. For example, to treat small collisions, we can think about atoms as rigid particles and not in terms of the nuclei and the electrons. But for very hard collisions, we need to think about the internal machineries and so on and so forth. So depending upon the energy scales, we can think about different degrees of freedom. And in that sense, the degrees of freedoms are also effective. I mean, both the field theory is effective, the degree of freedom is effective, all these things sort of go together. Okay? So once we have the degree of freedom, we need symmetries. Okay? We need to, as we found out in the context of electromagnetic theory, we need to say how the degrees of freedom transform under the symmetries that we want the system to have. Okay? And finally, once we know the degrees of freedom and the symmetries, we need to specify how the degrees of freedom interact with each other, obeying the symmetry. Okay, and that's like specifying the Hamiltonian. So usually we are concerned with short-range Hamiltonians with few degrees of freedom interacting at a time, etc. But that's essentially the information that if I want to describe a particular many-body system, I would have to describe these 3 ingredients to you in some detail. Okay, so that's how we go about it. And then let's choose give an example, and let's choose a classical degree of freedom. Okay, and what our degree of freedom are n component unit vectors, which we call classical spins. Okay, and they are residing on a lattice. Okay, so you can think about a lattice which is like a square lattice, a cubic lattice. Let's think about some. Okay, so that's my degree of freedom, and then I have some symmetries, and the particular symmetry, for example, I want them to be rotationally invariant. I want a global rotational symmetry, so which acts like a ON transformation, n-dimensional rotation, and I would like to have that symmetry. I may also want to have symmetries on the lattice, etc., etc. But to understand each symmetry I want, I need to give a relation like this, which tells us how the degrees of freedom transform under that symmetry. Okay, good. So various examples is that if you take n equal to 1, this is our Ising model where the symmetry is reduced to a Z2 symmetry, which is like flipping of positive to negative. If I have n equal to 2, I have 2 component spins, and that is known as the XY model. That's a good model of a superconductor or a superfluid, or also magnets of various kinds, and they have O2 symmetry. N equal to 3 is 3 component spins, and this describes Heisenberg models of various kinds of magnetism, and so these kind of systems we have in nature where the interactions are usually short-ranged. Okay, so so that's the kind of systems that we are going to think about. Okay, so we are not completely done yet. We need to remind ourselves of 2 things. One is that there is a UV regulator to the system. Okay, which is basically also the statement that the degrees of freedom are effective. If I try to probe them too deeply, I'll find that these degrees of freedom fall apart and new degrees of freedom emerge. Okay, so there is a lattice length scale in our problem. Okay, which is a UV regulator. In fact, there is also another length scale in the system, which is the size of the system itself, or the linear dimension of the system, which is the longest length scale. So this is the shortest length scale, and this is the longest length scale, and this is called the infrared scale, because the longest length scale translates into the smallest wave numbers. Okay, and the number of degrees of freedom is basically this. Okay, and as we realize that this is going to be a very large quantity, this is a dimensionless object, so we can talk about large and small. So this is going to be a large quantity. Okay, for our case. Good. So generally, what we are, I'm just going very fast because these are things that we know. Generally, we are interested in long wavelength average behavior. Okay, we are not interested in what each of these vectors are doing, but some averaged out behavior. Okay, and then what we want is try to probe this system in an intermediate length scale, which is the length scale of experiments or experimental probes, L. And often for the kind of experiments that we are interested in condensed matter or statistical mechanics, L is some intermediate length scale, which is much bigger than the UV length scale and much smaller than the IR length scale. Okay, and a physically relevant way to for all these things to fall, that there is a large set of such available length scale is when A over L goes to 0. Okay, and this is of course what happens in our systems. I'm just pointing out these things so that we can try to place them in the right perspective. Okay, and this limit is what is called a scaling limit. Okay, and so this average degree of freedom usually emerge in such scaling limits, and those are the kind of average degrees of freedom. They do not emerge only in this limit, but those are the kind of degrees of freedoms that we are interested in. Okay, the average degrees of freedoms that emerge in the scaling limit. Okay. So now you see that there are two ways of taking the scaling limit. Okay. I can fix the system size or box size and take the lattice spacing to 0. Okay. And I get this limit. And this is called the continuum limit. And this is the kind of limit that we started thinking about when we thought about Coulomb's law. Okay. So so then we started regulating this limit, and we thought that, okay, maybe for certain quantities we would be able to take this A equal to 0 limit, and then we did not do anything with the system size. We could have thought about a system with a system size of a box. We could do our electromagnetism in a box and put a big charge in the box, and still we would encounter these limits. And those kind of ways of taking a scaling limit, as you can see, is a continuum limit, because in some sense I am taking the lattice length to 0, or taking a finer and finer lattice. Okay. And then the other way of taking this same limit is fix A, which is like the condensed matter, more condensed matter way or statistical mechanics way, is fix the lattice length scale, or the average separation of particles, which is set by the density. Okay, inverse density rather. Okay, so and then I take L to 0. That's like taking a bigger and bigger system. Okay, so that's like taking the thermodynamic limit. Okay, so we can achieve the scaling limit, and depending upon the kind of problem that we are dealing with, and often taking these two limits gives us the same kind of averaged out degrees of freedom if we are cautious enough. And it's just that depending upon the problem, one limit might be more useful to take than the other limit. But at the end of the day, we end up with coarse-grained degrees of freedom, and those are described by continuum classical or quantum field theories. Okay, so that's the upshot of things that you must have learned in your course on the basic or advanced StatMech or similar courses. But these are the basic ingredients that we have in our system. Okay, good. So so what we want to try and do is try and see what happens in this case. So in our case, we can think about averaging these spins, okay, over, say, a box of size L, okay, and think about introducing this averaged coarse-grained degrees of freedom, okay. That's one way of doing things, okay. And then this average degree of freedom, okay, which again in this case is a vector, lives in a continuous manifold in R. Okay, so notice two things. This phi, we should not look very closely at phi. If I try to look very closely at phi, the concept of phi disappears. Okay, I get ends. Okay, so when I say that I define this coarse-grained variable phi, one has to remember that there is a length scale below which phi is not well defined, and that's a UV length scale. Okay. Similarly, this manifold R, which is a continuous, at the underlying it is a lattice, and we should not be able to, we should not look at it very carefully when I try to think about this concepts at the lattice scale. Okay, so it is true that we have a continuum field defined in a continuum manifold, but we have to make sure that we remember that there is a UV and IR length scale associated with it, which we should stay away from in terms of as is specified by this. Okay, so this formulation is valid only at intermediate length scales when we stay away from each of these lengths. Okay, good. So finally, the final things is that the symmetries of phi can be obtained in our case from the symmetries of n. Okay, in this case, it's a phi is a ON vector, And that's how we can obtain the symmetries of this coarse-grained degree of freedom from the symmetries of the underlying microscopic degrees of freedom. Sometimes it's easy, sometimes it's difficult, but that's the procedure that we need to understand to find out the symmetries of phi. Okay, so now I have the coarse-grained degrees of freedom. Now I have symmetries acting on them, and similarly from the interactions between m's, we can work out the interaction between the phi's, and this again falls under the one. To do this systematically, we need to do some kind of renormalization group calculation, but we will find that in our case the prescriptions by Landau in the form of Landau-Ginzburg theory, which was mentioned yesterday, shows us that symmetries alone and the fact that the interactions were short range tells us what kind of interactions would emerge for these coarse-grained degrees of freedom. Okay, so so in fact what we have are two manifolds. Okay, one is the manifold in which the R lives. So I have the coarse-grained degree of freedom at R. So this is where the R lives, and it is in D dimension. It's the Euclidean space of D dimension for an infinite system with open boundary conditions. Okay, but for certain reasons, it might be useful to think about periodic boundary conditions and large infinite systems, but with periodic boundary conditions. And there, this manifold is not a Euclidean manifold, but a torus. Okay, so for example, if it is a 1D system and if it is large, but I try to identify this thing, so I have a circle. In a 2D, if I take this sheet and try to identify these two and these two regions, okay, I get a torus. Okay, so this manifold, in which the system lives, which is called the base manifold or the domain manifold, okay, is either typically an a D-dimensional Euclidean manifold or a D-dimensional torus. Okay, and the other manifold is this manifold in which the phi lives. Okay, in our case, it's an ON vector. Okay, which came from symmetry. Okay, this is important that it came from symmetry. Okay, we call this the field manifold. Okay, or the range manifold. Okay, so we would have to deal with these two kinds of manifolds, and the particular problem we will be encountering is classification of closed paths from both in the base manifold and in the field manifold. Okay, and how to connect them. Okay, so we know these two. We can use our homotopy theory to classify, but the physics question arises: how are these classifications of the base manifold, the closed paths in the base manifold and the closed paths in the field manifold are related? Okay, so that's roughly where we would like to end. I would like to show you one slide, which is what we would like to take up, is the context, the amazingly diverse context in which all these questions arise. Okay, so the particular thing that we would consider is the symmetry breaking order parameter field. As you have seen from my the example that I gave, is geared towards that. Okay, and I'll deal with from tomorrow onwards. I'll deal with the symmetry breaking order parameter fields and trying to connect the classifications of the base manifold and the field manifold, the closed loops for these kind of systems with for magnetic systems and also for crystals. Okay, but of course this is not the only kind of manifold that we know in the kind of things that we do as physicists. Okay, in fact, the many body wave functions of quantum mechanics themselves form a manifold. So again, the base manifold is R to the power T for particles, and then the psi of R1, R2, that specifies a manifold, which is of course a complex type, but that lives in the Hilbert space, but that's one kind of manifold. And trying to understand this classification gives us an understanding of topological phases. Okay, and just as a remark that the Hilbert spaces of two identical particles in different dimensions would give us an understanding of bosons, fermions, anyons in 2 dimensions, etc., etc. Okay, for the velocity of fluids. Okay, if I try to ask this question, where we would encounter vortices and their classifications and various non-Hamiltonian extensions of these ideas. Okay, we saw some for the electromagnetism, where we saw the monopole. We could go on and ask various kinds of questions that some of you may have heard these words. But essentially, these are questions of exactly of the kind that we are on the verge of discussing, and these can be generalized to various field theories. And what we will do from the next class is concentrate solely on this, okay, and on classical systems mostly, okay, and try to understand the connection between the classification of the two manifolds, the order parameters field, and which forms a field manifold, and the base manifold in which the system lives, and try to see their effect in terms of unconventional phases and phase transitions. Okay, this would be what we will do for the last 2 class, and we will understand topological defects. Okay, and their role in phase transitions. Okay, good. So I rushed a lot, but I think these are things that you generally know. But okay, so let's take questions. Yeah, so I think I have answered this question. Oh, sorry, there was a question that I missed from Steffi Jules. Can you define manifold again? I'm extremely sorry I missed this question. So manifold is a set. Okay, so manifold is a set. Okay, set. Okay, which looks locally looks like Euclidean space RD, okay, or complex space C. Okay. Now, so since if it looks locally like this, then locally, so we know that these are differentiable spaces. Okay, so we can perform differentiation, integration, limit, etc. on these kind of things locally. Okay, so locally it is differentiable, and since it's infinitely differentiable, it's continuous and it's infinitely differentiable. So locally it looks smooth. Okay, so all examples. Think about all smooth curves or smooth surfaces that we have, okay, are examples of manifolds. Okay, so that's roughly the definition. So one thing that you would like to think and maybe define is that what happens if you have a hole, okay, like this. Okay, so when you think locally, should I take this hole, or how should I draw? Okay, so therein we need to define the concept of open set and closed set, like should I take these lines right on the hole and or not? Okay, those are more sophisticated ways of trying to understand these issues, and yeah, it's possible to extend this, but yeah, that's more mathematically sophisticated way of classifying manifolds. Okay. There was a question by Tunir, which yeah, so f.g, that's the sorry, what does, yeah, it depends upon whether so the question that Tunir is asking is that whether f.g is equivalent to f. Okay, it depends upon whether f or g belongs to the same equivalence class or not. Okay. Yeah, there was a question by Purnima. Are there infinite base points in a manifold? Yes, depending upon, there are infinite number of base points in a manifold, and you can choose any one of them. And using this path isomorphism, you can try to reconstruct other manifolds at other base points. Okay, good. So, okay, so I think today's lecture, okay, there seems to be another question from Orko. Is there a general prescription for identifying intermediate or post-grain length scales? I don't exactly understand the question, but I think that the length scale at which you want to probe the system, okay, controls this intermediate length scale. Okay, so suppose you want to do an experiment, okay, what is the length scale at which you want to do that experiment? Okay, that determines at which length scale you should probe the system. Okay, we know that length scale has to be away from this UV or the IR length scale, but in general, as long as that's satisfied, and this is satisfied because L over A is much larger than 1. Okay, that's guaranteed. All we want is that there exists such length scales. Okay, and then one can use different experiments to probe that. Okay. Okay. Yeah. More questions. Okay, if there are no more questions, then let's wrap up today's proceedings. So what we will, so tomorrow, I'll urge all of you to sort of brush up your Landau-Ginzburg theories so that we can go ahead without trying to derive too many things in Landau-Ginzburg theory. Okay, that should be fairly easy, given that you have all encountered Landau-Ginzburg theory in some form or the other. Okay, good. So,
can you, I mean, maybe mention some like simple or like a topology book for physicists? I mean, a good.
Yeah. So I have been developing a set of references which I'll at the end of the. Is it okay if I supply it at the end, because I want to sort of demarcate which areas one should try to understand from which source, or do you think that I should do it right now?
I mean, if you can just give one like sort of standard reference.
Yeah. So I think that for the kind of things that we are doing, there are two references that I personally find very helpful. There is a RMP by N.D. Marmin. I think it's from 1979. Okay. It's topological defects. It's called It's called topological defects of ordered media. Okay. The problem of with this is that, as you can see, it's quite old and it lacks some modern perspective that we are trying to understand. But then the other thing is there is a book called by D.J. Thaulis, okay, which covers more. I think it's a book more recent, 1990s, which is called Non-Relativistic Quantum Numbers. Okay. And of course, if one wants to delve into a lot of details of the logical structures, then there is the book by Nakahara, which is, I think, a good book. And then there is a book by, okay, I don't remember the exact spelling of the author, so I shouldn't write. Okay, so, but I think that various things, I would give you a list at the end.
Okay, yeah. So
Okay.